I'm going to introduce you to deep learning, which is a subfield of machine learning. So before I start, is there anyone that has done something with machine learning? Anything? Ooh, very few people. That's cool. You're in for a treat, I think. I'm going to talk about Joey. Well, that's the name I gave to my bot that I'm building. I'm actually trying to build something of a digital assistant that's going to help you with things like your administration of hours worked or questions that you might have around your work, or calling in sick to work. You can do that too in the near future. Today I'm just going to show you how it can answer questions that you might have. And I've done something special. Well, I think it's rather special. I downloaded the FHQ from the local airport, and I put it into my bot yesterday. It's the first time it's talking English. Normally, it's talking Dutch, so you will have to excuse me for the bad results that it might give. But let me show you what it is before we do anything else. Let's fire it up and see if it works today. There he goes, parsing Java, doing a lot of stuff. This is, by the way, a Spring Boot application. This is the part that you can chat to. I will show all the code later on. And it's not helping me. Okay, let's move on quickly. I was going to show you that this is basically a REST interface where you send a piece of text to in the form of JSON, and it will answer your question something like, where are the check-in areas? And it will give you the answer, well, they are over in a certain place in the airport. It's a very basic Q&A bot that we're going to build today using deep learning. So what is deep learning? Deep learning is a subfield of machine learning. If you have done machine learning, you will probably know that you can use linear regression, which is a well-known term from machine learning. Basically, that's the most simple model that they use for teaching you about machine learning. This goes beyond all that classification, linear regression, all that basic stuff. That's not the thing I'm going to talk about today. But still, I'm going to try and teach you a little bit about how neural networks work. Because that's the thing that we're talking about. Deep learning is about neural networks. The idea behind this is that they looked at the human brain for this. It's kind of funny, because the human brain is actually pretty digital if you look at a single neuron in your brain. You have a few billion of them. My network has about maybe a few thousand, and that's it. But the idea behind this is that we're trying to model a computer algorithm according to the structure of a brain. So how does it help you answer questions? That's a big theme of my talk. I'm going to propose an idea where I will say, well, when you look at answers and questions, you can say there's a connection between them. Somehow there's a relationship between the question, where are the check-in areas, and the answer, they're over there. Right? So far, so good. It's a pretty simple idea. My hypothesis is that I can convert questions into patterns, numeric patterns, that I then can match to an answer that belongs to it. Basically, what I will say is some pattern times another set of numbers, any numbers, I don't know yet, equals a specific number. Let's say the pattern of question number 1 times a few weights, numbers, random chosen numbers, equals to the answer number 5. That's what I'm going to try to do today. So how does it work? This picture, I think most people will know this from the internet, these kind of pictures. Anyone hasn't seen this sort of structure before? This is called a neural network. And what it is, it's basically a network structure, a graph. You can look at it that way. Normally we don't do that in software, but this is what it looks like if you would like to visualize the structure of a neural network. All these round things you see, those are the neurons in the network. The most left side of the picture is the input layer. And the input layer is where you provide the input. The pattern of your question is going there. The middle layer is called the hidden layer because you can't see it normally. We can visualize it using debugging tools. I will show that later. But normally, this is the place where the magic happens, so to speak. And you can have one hidden layer, 0, that's also possible. And you can have hundreds of hidden layers. There are neural networks in the world that are used for synthesizing human speech that have hundreds of layers in them. So this is sort of an idea. This sort of structure helps to make complex formulas that multiply my magic numbers with the pattern of my question. That's what's going on in this network. And the final layer of my network is the output layer. This is the layer that contains all the information to select the right answer in my set of answers that I have. So this is the basic structure of a neural network. Now let's go a little bit deeper into what a neural network does on the inside. I'm doing this without, I'm doing this because I think you should know this before you can build neural networks. Later on you will see that in the end, it doesn't really matter all that much because you don't manually do this kind of stuff. So let's look at a single neuron with a few inputs. The dot is still the neuron. On the left side, I've drawn a few input neurons. This is called the input layer. Every neuron has a number of input connections. Those are the lines between the x1, x2, x3 to the neuron itself. And every edge in the network has a weight to it. Basically what we're doing is the output y is a activation function over the sum of all the inputs multiplied by their weights. It's a simple calculation actually. It's y is weight times the input plus a certain bias that you could use normally. And we use an activation function. And why do we do that? Because actually I want the output of this neuron to be between 0 and 1. We're going to calculate zeros and ones. That's basically what we're going to try to do. And you can think of it this way. If you multiply 1 times 5 and you put that to the output, it will become 5. That's not very desirable because we want to be between 0 and 1. So what you do is you can call up a mathematical function called sigmoid, and what it does, it converts it to a value between 0 and 1. So that's why we have the activation function in there. Trust me, if you have the feeling, well, that's a lot of math, yeah, it is. Don't worry about it. You will later see that you don't need to know all this math from the top of your head. So this is how it works. And what happens is we are going to try to do a trick with this because I don't know the weights of my inputs beforehand. I only know the input itself. That's the pattern of my question. And I know the output. I know that I have a certain pattern that it belongs to a certain answer. That's what I try to teach the computer. So I know the input, I know the output. I just don't know how to shape the formula that is needed to convert the input to the output. That's what machine learning is about. Trying to estimate a mathematical function that clearly identifies the relationship between my input and the specified output that I know. In normal applications, you would say if the word X is in the text, then it's probably this answer. If word Y is in the text, then it's probably that answer. That would be another way to do it. But it would take you hundreds of years, and it's not very exact. Still, as you can imagine, if you're trying to guess numbers for this kind of formula to express the connection between the input and the output, it's still not going to be very accurate, because I could be wrong. That's also one of the things that you have to keep in mind with machine learning. Your model will be wrong at the end of the time, at the end of the day. But how wrong? We'll have to talk about it. So how are we going to teach the computer the connection between my question and my answer using this mathematical formula? First step is to actually try to run my network. So we'll take one question with one answer, and I will run the question pattern through my network and just choose a few random numbers for the weights for each of the connections in this network. And all numbers are random between 0 and 1. Why? Because I have to choose something. This is the first pass. We call this the feed-forward pass in the network. The second pass is a backpropagation pass. And this is where it gets hard for the computer. Because what do we need to know? Well, we need to express a goal. Why? I need to know that when I do a feed-forward pass through my network, I produce a certain answer. And that answer is wrong 100% of the time, or I might get lucky. That can happen too. I need to express a way to tell my computer, well, you're this much off from my answer. That's basically what I want to express. So we do this using a loss function. And this one on the slides is a simple one. As you can imagine, if you have a complex problem like I have 120 possible answers, and I need to know how far off I am based on those 120 answers, you get a much more complex loss function. But for the sake of this presentation, I will keep it simple. Basically what I'm saying is, well, the error rate of my network, how far am I off, is expressed as the answer that I've given, the number that is outputted by the network, minus the one that I expected it to be. And then there's a second trick that I like to do, because when I just say, well, I got the answer 10, and I expected 12, that's 2 off. And the other one is minus 2 and plus 2 maybe, 2 answers. When you average that, it's 0. And my network is perfect. It says, wow, cool, I'm working. But that's not correct, because 2 answers were wrong, but they canceled each other out. So what I do is I use a quadratic function. I say, well, do it to the power of 2. And what happens is every negative number becomes positive. And when I'm a little farther off, I will punish the computer more than when I'm close. And it will be exponential, the farther away I get from the right answer. So this is the kind of thinking that goes into defining what my network should do. If I need to express a goal, I want to predict the temperature of a machine, and I need to define how far off am I, then this is one of the functions that you can use for that. Now how to optimize it. How on earth am I going from this goal to something that I can optimize? And there are 2 ways to do this. And I'm going to tell you the first one, which is totally random. Can anyone guess what happens if you use random numbers all the time? And you try this for 100,000 times. Any ideas? It might not work at all. I don't know when did I reach the right solution. So that doesn't work. There's another way to do this. It's called gradient descent. And it works like this. When you plot the loss function based on the weights that I configured in my network, you will get a graph that looks like this. It has 2 mountain hills and 1 valley in the middle. It's oversimplification, but this is what happens. This is what you see when you try to plot one of the weights in a neural network. And as you can see in the middle, there's a dip where it's optimal. It doesn't reach the bottom of absolutely 0, because that's impossible. In machine learning, there's this notion of a solvable error and an unsolvable error. And the unsolvable error is the one that you see in the chart at the bottom of the chart. It never reaches 0. And why? Because Mars is in the incorrect position. The stance of the moon is isn't optimal today. The sun has a radiation problem. I didn't eat too many tapas yesterday. All kinds of reasons, and we don't know them. It doesn't matter, but I want to make it very clear to you, your model is going to be wrong at the end of the day, but it doesn't matter all that much. So how do you reach this valley in the middle? That's a big question. It so happens to be that you can calculate a gradient of the weights. How much are the weights decreasing or increasing? There's a mathematical trick for that. I call this a trick because I'm not very good at math. So I just look it up on the internet, I try the formulas, and then okay, I'm getting somewhere. This is a cool trick. When you follow the gradient down, you will get in the valley. That's guaranteed. How fast this is going depends on how you do it. So what we'll do is we choose a random initial weight, and we calculate the gradient, and we will step by step follow this gradient into the valley. And as soon as we're in the valley, we will say, okay, stop, we're there. And when do you know you're in the valley? When the weights start to increase again, the error rate. So this is what the computer is trying to do. What you need to do for that is convert the error rate function into one that actually is differentiable. We're going to create a derived function from the error rate, which ultimately gives us the gradient. And the thing is that we have two unknowns in this case, the W and the B. Those are both unknown. So what you have to do is another trick, is you don't have to create one derived function for this, but you have to create two, because of the two variables. You derive for one of the weights, and that gradient you're going to follow. And you derive for the other weight, and you're also going to follow that gradient. And you do this for 10,000 times at least. Why? Well, when you descend the gradient, you can do this by the delta you're calculating using the derived function. We do this one time, we'll get a delta, and we follow that down the hill. But if you do that, something very interesting happens with your computer. It will reach the bottom of the valley, and it will jump to the other side, to the mountain hill, and it will climb up and go into infinity. Something very weird that happens. So what we do is something that's called the learning rate. And the learning rate is a number, very low number, 0.001, or even lower than that. And you multiply the delta by that number and use that as the next step in your weight update. Why is that? Because if you move slowly, you won't miss the bottom of the valley. If you move fast, you will run across, and it's basically flying a kite down the mountain, a parachute, or even an aeroplane into space. That's a sort of equivalent that happens. So set the learning rate too high, you will miss the bottom. Set them too low, and you won't reach the bottom in 10,000 steps. So it's sort of the feeling that I want to give you what happens in a neural network. And it becomes more interesting because this happens one time for one neuron in my network, but I have several. In my Q&A network, there are 2,500 input nodes, about 2,000 hidden nodes, and 80 output nodes. So as you can imagine, this times many thousand neurons in your network. That's what happens. And talking about it, in my laptop, there's a pretty good graphics card. Why do we use graphics cards? Because if you have to do this on 1.5 million times 10,000, you can imagine that it takes a very, very, very long time to train. And it gets worse. If you're trying to synthesize human speech or anything else that requires hundreds of layers in your network, you can imagine that you're not training a few minutes, but a few weeks or months. So people were starting to think, well, how does this work? And there's an interesting property to neural networks. You can express a whole neural network in terms of matrices and vectors. And the graphics card happens to be very good at calculating matrices and vectors. So what do? They push all the data in the form of a matrix or multiple matrices to your graphics card, They program the gradient descent algorithm as a shader on your graphics card, and everything gets sent off to your NVIDIA or whatever graphics card you have, and let that calculate what you need to know. And it's very fast. It's 100 times faster than your CPU, depending on your graphics card, but mine is a GTX 1080 in my workstation at the office. It's pretty fast. 8.4 teraflops in a single graphics card. When I started doing neural networks, I was like, what? I don't know all this math. And you don't know either, probably, unless you've studied statistics and machine learning. But don't worry, you don't need to know all the details by heart. What you need to know is a loss function. How do I define a loss function? And trust me, there are many existing loss functions that you can use instead of building your own. So look it up rather than finding out yourself. And you need to know how to set up data for your neural network. So let's talk about that next. But before I do that, let me show you how it works in code. Yeah, you can read the code. So, how does a neural network work in Java? There's a library, Deeplearning4J, that allows you to define a neural network in the layers that I just showed you in the diagram. That makes it rather easy. If you're talking about products like TensorFlow, which you probably have heard about by Google, they use that to build AlphaGo and other very amazing neural networks. Those tools work with matrices and vectors, so it's very low level. You have to know the math to use them. But I think that this is better. Deeplearning4J allows you to define a neural network in the layers that it has. Underneath it's still matrices and vectors, but we don't know all that, and we don't have to. What you can do is you can say, well, I want to build a neural network, a multi-layer configuration for a neural network, and I'm going to say to the computer, well, I want a number of layers in my neural network, and I can just define, I can say layer number 0 is my input layer. It has a rectified linear activation function. What that even means doesn't matter much. You can just look this up in the manual and think, well, yeah, I was sort of thinking of not going from between 0 and 1, but just do me from 0 to plus infinity, I don't care. It's analog in that sense. And I could say, it has to be as big as the pattern that I want to put into it, and I have 1024 hidden units. How do I get that to that number? I will talk about it later. It's basically experimentation. That's all it is. And I can say, well, I have a layer number 1 with a softmax activation function, and this is an activation function that says, well, when I have 10 output nodes, only one of them can reach 1, and all the others will go to 0. So the total of the nodes is a value of 1, and I'm going to distribute that value of 1 over the nodes. And basically what you do when you want to select the right answer, you will pick the node that's activated the most, with the highest value in the output. That's all I'm doing here. And what I will say finally to my network is, do a backpropagation algorithm, so you don't have to build that yourself. It's just there and use it what it's good for. And I don't want to pre-train my network. And that's basically it. It's just a number of lines of code to define a network. Actually, I could get away with 4 lines of code here, 5, if I include the nasty builder thing at the top here. And that's basically how you build a neural network in Java. It's smaller than you think when you look at the math that is involved behind this. And what happens when you call build on the neural network, it will set up all the matrices, all the vectors, all the crap that I talked about without you knowing that it's there. It's pretty intelligent about it. And now what I can do is I can start to train this. And what it does, it uses a number of answers and a number of questions. This is it. And it reads them, factorizes them, and runs them through the network, and you will get a trained network. So how do you train? Well, let me look over here. Training the network works like this. I first, at the top of the code, I load the labels, basically the index of the answer that I want to give, and I load the questions in the form of vectors. I will get back to how you get those vectors, but that's what happens. And I will tell my network, well, fit these features and answers on each other. Try to estimate the weights for my formula, and that's all I'm asking. And it will take a few minutes to run, and what you will get back is a trained model that you can save on disk and keep for later use. But you could use the model directly if you want to. That's basically what it does in Java. I'm not going into much detail of deep learning itself, because I think that once you start doing machine learning, you will quickly learn how to use this framework. It's mostly, the most important thing is the multi-layer configuration. That's what you use to build a network. Once you have a network, you can call fit on it, and it will run your training data through it. I think it's much more interesting to look at the training data later on instead, because that's much more complicated. The network itself is basically, yeah, you could say random numbers. But how do you get those numbers? Well, there's a trick for that. Converting words into numbers is a method of, well, I pick a word, the first word, hello, I will assign a number to it. I get a second word from the same sentence, it's a world, I will assign index number 2 to it, etc., etc., etc. For every unique word that I find, I assign a new index to it. This builds a vocabulary, and it's approximately, depending on how much questions and answers you have, it could be in the thousands of words, but that's no problem. I can use that information, once I know how big my vocabulary needs to be, I can use that to shape my neural network, how big it needs to be on the input layer. And when I want to answer a question, I take the same vocabulary and I try to match the words from the question on the indexes that I know. If I don't know an index, I will assign 0 to it, and I will tell the computer, I don't know this word. It doesn't matter much, because what happens is that these numbers, these indexes, will be converted into a pattern. And patterns can vary slightly. That's not a problem for a neural network. That's why you have the hidden layer of such a big size. The general intuition is that it tries to follow a certain pattern, and when your question is close to a certain pattern that he learned, the network, you will get an answer. It might be wrong, but usually it isn't. So first I assign indexes, then I assign numbers to words, and I create a vector of the size of the vocabulary. So each word is this big, very, very, very large. But only one element is on 1, and the rest is 0. And I do this for all the words in my sentence, and I get a big matrix that I can use to train or later answer questions. So once I know that, I can say, well, this pattern matches to this answer number 1, the other question matches to number 2, etc. Now I'm going to try to live train my network, so hold on. It might go wrong. So let me show you what happens once you run the program. Oh, this is a service application, I need the other one. So this is one of the tools that the Deeplearning4J comes with. I will have to check what happens. No, it's not working. Give me a second. As you can see, I'm switching out backends for my Deeplearning4J. Deeplearning4J is capable of training your network on the CPU or on your graphics card, so you can switch between them. And it makes a big difference in performance, what you use. And Deeplearning4J itself is actually split up in several parts. So you have a part that's called NLP, which is meant for language processing. And there's a core part that just does the neural network thing and nothing else. So you'll have to check the manual on the website to find out which parts you need. There are many parts to this. So. Well, it's still not. Normally, what you would see here is the weights update in the top left chart. You will see a line that goes down, 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 almost to 0, which is the error rate of your network. What you can also see in this page, and I hope that it works today, is the visualization of your network. It's all failing now because I don't have an internet connection that's properly working, and it doesn't download my backend properly. So that's unfortunate. I will post a picture of it on Twitter or a video on YouTube that demonstrates this. But you can debug your neural network using these tools. It's quite useful. And I can only recommend this because neural network building is a tough job, I can assure you. So basically what happens in my program is I convert a question into a vector, a pattern, and I feed it through the network, and what it will produce is another output vector of size my number of answers that I know, and one of them is the highest. And this is all between 0 and 1. What does this tell you about the accuracy of your network? Well, it thinks, I'm 80% sure that this is the right answer, or I'm 40% sure that this is the right answer. That's basically what it's trying to do. And it makes it interesting. When do you give the answer to the user? Is it only above 0.5, or do I always give it? That's the sort of thing that you have to think about when you build this sort of software. Ultimately, you grab the highest one and you show the answer to the user. That's the idea behind the program. But wait, there's more to this. What if I told you that it takes you several weeks of experimentation before you got something that works? I mean, it's only a few lines of code. What could possibly go wrong? That was my thinking at the beginning. But it's seriously black art what you're doing. It so happens that because you choose your initial weights randomly, you get different results every time you run your neural network training. And that's quite annoying, I can tell you, because you're thinking, well, the first time I got 64% of the questions right. I want to go to 99% because that's what people expect from me. So what can you do? Well, I'm going to change something in my network, but yeah, weight initialization changes for the next run, and you got 55%. Oh, crap, what happens? So there's a cool trick for that. As everyone knows, random isn't really random in a computer. So that's why you can configure a seed for your random number generator. Please do, if you are going to try this. Put it to 42 or 1337 or 0 or 100. I don't mind what you choose, but fixate the random number generator of your computer so you get something that's predictable, sort of predictable. Also, loss functions have a quite profound effect on how well your network is going to do. So pick one that you think expresses your goal the best. So for example, when answering questions, I would like to use a loss function that expresses the difference between the answer given and the expected answer in terms of classes rather than absolute numbers. There's a standard loss function for that. You can find it on the website. I will show you in a minute. When you choose something that expresses a linear relationship and you use it for classification, it clearly doesn't work. That's important to keep in mind. So look it up on the website. Try to figure out what am I actually doing. Am I building a classification network or a prediction network for something like temperature or something else? But pick the appropriate loss function. And there might be multiple ones for the same kind of problem. Experimentation only tells you what could go wrong or works. Also, I showed you just one optimization way, gradient descent. There are various variations on this topic. So there's stochastic gradient descent. There's a optimizer called RMS propagation, which is a optimizer that slowly decreases the learning rate as it goes along. Why you want to do that? Well, sometimes that helps to reach the bottom of the valley. So you will have to experiment with the optimizer settings of Deeplearning4J and find the right one for your job. Also, the number of epochs happens to have an effect. What's an epoch? Well, when you train a neural network, basically what you do is you run all the data through your network, and it's called one epoch. And you try it again, and there's another one, and another one, and another one. You can run your same training set 1,000 times through the network, and it will get better and better and better and better over time. But there's a sort of a cutoff point. Beyond certain number of epochs, it will stop learning, or it will overfit. It will get worse. So that's important to keep in mind. And the learning rate I showed you in the valley, you can easily miss it if you have a wrong learning rate. So how do you find out what you should use? Well, there's a website, Deeplearning4J. It has all the sorts of documentation. It says all about the kinds of neural networks that you can use. There is information about visualization, monitoring, debugging, but also, let me see, early stopping, all sorts of things. The loss functions are also documented here on this website. You can just look it up and pick what you need. So that's my message to you. If you ever want to try this, first try to familiarize yourself with the loss functions that exist. Find out what you're exactly building and choose the appropriate loss function. Then start to tune your network in number of hidden layers, number of neurons in your network. I can't give you any guidelines on this because this is a black art. And it's funny, if you read scientific papers on this subject, the scientists will tell you, yeah, we got state-of-the-art results. Go do a Google search later today and check that. You will be amazed. People say state-of-the-art results, which practically means it's a black art. They don't know. And when you read the paper, that's the kind of fun thing I like to do, then you will see they don't tell you which parameters they used, which optimizer they used, which layout they used. They don't tell you all that. And they even don't provide you the code. So it's fishy, at least. So deep learning is a black art, but once you know that there's gradient descent involved in all kinds of neural networks, and you know which loss functions you need and how to set up a network, you're golden. Start experimenting. That's my message. If you want to try it out, I have it on GitHub, so you can download it. It's ready to go if you have the right setup on your computer and a working internet connection. And if you're interested in a very, very basic introduction into machine learning and deep learning, there's an excellent series on YouTube, Deep Learning TV, and they tell you all about how the gradient descent algorithm works. They go over all the nasty details of neural networks. Yeah, so that's a recommended reading, I would say. Cool? And you didn't expect this one, right? I'm Willem Meints. You can reach me on Twitter. I'm a technical evangelist for info support, and I'm a Microsoft MVP, which means it's a sort of equivalent of a Java champion, but for Microsoft. So don't burn me today, please. But if you have any questions, please, you can ask them now or you can ask them later. I don't mind. With that said, are there any questions?
You showed us deep learning for Java. It's one popular library. There's another popular one framework, which is Apache Spark. I don't know if you've experimented with it and what are the main differences. Can you do neural networks in Spark? And just some brief.
Indeed, you got two tools in the Java world, Spark and Deeplearning4J, but they are totally different from each other. Apache Spark is a big data processing tool. Obviously, neural networks are also in the big data field. You need a lot of data to get this right. But Apache Spark has the basic machine learning algorithms, no neural networks. However, you can use Deeplearning4J in combination with Spark, which gives you the opportunity to use multiple machines to train one neural network. So there's a combination possible, but it's very different from each other. You can use a single layer neural network to build something that Apache Spark provides. For example, linear regression is a single layer neural network with a linear activation function. It's what happens to be. That's practically, you can do the same thing, but Spark is different in setup. Yeah. Cool. Any other questions? No? Cool. Well, thanks for listening.